All right, so today, combining functions. This is going to be pretty straightforward stuff. I think you've seen a little bit of it. We'll do this thing kind of using three different approaches. Okay, we'll use an analytical approach using algebra. We'll talk about how we can use like kind of a simplified version of that as well, kind of just the evaluation process, and then we'll do a graphic approach. Okay, so not too bad. I think again you've seen some of this stuff. We're basically when we say combined functions, it's finding the sum of differences, products, and quotients of those things. Okay. Doing that first, there's something to think about. There's something to recognize. You don't write this down. But the two functions f and g can be combined to form a new function, f plus g, f minus g, f times g, f divided by g, or g divided by f, or g minus f. Okay. In manners that are similar to how we add, subtract, multiply, and divide, just real numbers. Okay. But there's a notation here. You're going to hear me say f plus g a lot of times instead of f plus g of x. But when they write f plus g of x, okay, like they wrote here, okay, we can actually separate those and say that it's f of x plus g of x. All right. But this only works for values in which both of these functions are defined for. So the x value has to be part of the domain for both of the original functions f and g. Otherwise, this will not work. Okay, the sum or difference cannot be found, or product or quotient cannot be found. We'll talk about that as we move forward. But you're going to see the idea that if I want f times g of x, that is the same thing as f of x multiplied by g of x. Okay? Same thing with subtraction, division, that kind of thing. Does that make sense? You can separate it into these two separate functions and then multiply those separate functions together. Just kind of give you a simplistic version of what we're talking about here. Let's go to, let me insert a slide here. Let's just say f of x is equal to 2x plus 3. Let's say g of x is equal to x squared. If I wanted to multiply these things together, let's say that we're looking for f times g of x. Okay. We can rewrite that as f of x times g of x. So what if I was, and this is the idea, what if I'm interested in a specific x value? What if I'm interested in like x being 2? Okay, so I'd be asking f of g of 2. Well, that should equate to f of 2 times g of 2. Does that make sense, everybody? Okay. Well, what would f of 2 be? What would I get if I plug 2 in up here for f? 7. What would I get if I plug 2 in for g? I get 4, right? What's that product? 28. Okay? That's the idea that we're doing when we break it apart as f of x times g of x. Okay? When I leave it as f times g of x that way, that idea is this, guys. If I were to take x squared, multiply it by 2x plus 3, will that give me 2x cubed plus 3x squared if I distribute that stuff through? Okay. So this is kind of an algebraic rule for f of g of x, or f times g of x. Okay. So now what if I wanted to evaluate that at 2? Well, that would be 2. Now, putting 2 in here, so it would be 2 cubed, right? Plus then 3, and then 2 squared. So what's 2 cubed? 8 times 2 is 16. What's 2 squared? 4 times 3 is 12. What's that give me? That's the same value we found that way. Okay? So we can evaluate, we can find a new function and evaluate that new function at 2, or we can evaluate the original 2 functions separately, all right, and then multiply those outputs, okay? And both techniques, guys, are techniques that we're going to want to develop proficiency with, because sometimes it makes sense to do what we did there on the left. If 2 was the only function or only value I wanted to evaluate here with this product, then this is probably the approach that I would use. If I had a list of X values, so let's say that we were trying to fill in a chart, okay? Got my X's, and then over here are going to be my F times G of X's. If I wanted to try, those 6 values, okay, I probably don't want to do this route here, okay? I probably want to develop this rule, and it might be easier to evaluate those 6 things with that rule. It might be quicker. Does that make sense? Okay. It might also allow us to kind of access some technology and find those values easier with technology. Okay, because we have our table abilities within our TI-83, Day4. GeoGebra has a table. I believe we can go over here somewhere. Yeah, go down to Relation and Function Inspector, and I believe that gives you tables at some point. I don't know. You have to mess around with it. I'm not sure what the like command codes are for doing that. But if we had to evaluate multiple places, developing that rule is pretty essential. All right. So something we can do. All right. One thing we want to think about though is F plus G. Is that going to equate to G plus F? Are those 2 things the same? Okay. Remember, these are functions, but they are the same. And that's because addition is what property? Commutative. Okay. Now here, I go F times G is that's the same as G times F. Yeah, because multiplication is commutative, right? What about F minus G? Is that going to be equal to G minus F? No. Okay. Subtraction is not commutative. And what happens is that you're going to recognize, if I take, just do it with some real numbers. If I take 5 minus 2, you get 3, right? Take 2 minus 5, you get negative 3. You get the same value, you just go on different sides of 0 now, right? There's some quantity. That's what happens here. You're going to see that if I take and graph F minus G and compare it to G minus F, it's actually a x-axis reflection of itself. Okay? Transformation, because we can develop that negative on one side. For the same reason, G divided by F, obviously 2 divided by 5 is different than 5 divided by 2, right? These 2 operations are not commutative. And that's kind of a concept that they usually ask, maybe in a homework or a quiz or a test, instead of just allowing you to know what you, or show what you know through arithmetic. They'll say, okay, now that we've done this, and you recognize that when you evaluate F minus G and you evaluate G minus F, you get different answers. Well, why are you getting different answers? And the answer to that is because subtraction is not commutative. Okay? So they might ask those kind of math, kind of intuitive questions so that you can see those properties existing and how they operate and work for us. And that happens a lot through other aspects of mathematics. We're going to be very interested in talking about whether operations like these are able to be flipped, okay, and still get the same results. So now this, okay, so this says these functions, guys, they will only work when we combine them through addition, subtraction, multiplication, division. They only work for the x values that both or all the functions are defined for, okay? And our rules here, guys, are kind of developed based off of the simplistic, most simplistic version of adding, subtracting, multiplying, dividing functions, and that means that we're just using 2. We could use 3. We can multiply 3 functions together. We can multiply 4, 5. We can divide multiple ones. We can subtract 2 or 3. Does that make sense? We can add 2, subtract 1. We can combine all of our functions just like we combine real numbers. But the idea is that if you're going to be looking for output values, okay, you're looking for range values, then you're only going to develop range values when your input values work for F and they work for G at the same time, okay? So that's why they're saying when we find a domain, of our new function, you see how they're writing it. Oh, sorry. They're writing the rules that we developed in the last slide on the left. Okay, so you got F plus G of X, they made F of X plus G of X. Well, you see if they said a domain is A intersect B, where A is the domain of F and B is the domain of G. Okay, capital letters like A and B. We were working in what we call set theory. It is how we identify a collection of things. Okay, so how we label sets. Okay, or identify sets. So set A is just the domain for F. Set B is just the domain for G, and that intersect symbol means it's where they overlap, right? It's the values that are shared by both. It might be eventually a good idea to have a picture when you're doing these, okay? Especially when our questions are targeting the domain. Notice all of those are F and G, right? Okay, so it's the same two functions, F plus G, F minus G, F times G, F divided by G, and so forth. When we want the domain, if I find the domain of F plus G, then I have the domain of F minus G, I have the domain of F times G, and I have most of the domain for F divided by G. The only thing with F divided by G we got to pay attention to is that we cannot have division by 0, right? Okay. Also, understand how, F divided by G is going to provide me a domain that's a little bit different. I got to make sure that I don't have 0 in the bottom. But if I did G divided by F, G divided by F's domain may or may not be the same as F divided by G's domain. Does that make sense? Because you have a different function in the denominator. You might have different places of division by 0 when you do that. Okay? So that weird notation down there, kind of read this. It just says the domain are your x values, and our x values are coming from the real numbers. Okay? But they are elements of the domain A intersect B. Okay? So they're elements of the overlap between the domain of F and the domain of G. Okay? But they're putting that vertical bar, and they're saying such that G of X, that denominator, is not 0. Okay? So that's just kind of basically what they're doing there is they're saying the same thing they said in the top 3. Domain A intersect B, domain A intersect B, domain A intersect B, domain A intersect B, except for you can't divide by 0. That's what that last statement is saying there on that right-hand side. Is that all right, everybody? All right. I think it's important when we see things, and we haven't really dealt a whole lot with that type of notation, to be able to read that and analyze and talk about what are they actually saying with that. I think that's a huge part. You heard me say this before. Notation is extremely critical to any math class. I think that's important to discuss and talk about. All right, so let's take these two functions and let's kind of mess around with them a little bit and determine domains for them. We'll determine what F plus G is, F minus G, and we'll do that in a couple different ways. So this will take like a bulk of our time. And this is very similar to some of the questions you see in your homework. The main concept they ask in our homework is if we can, with two functions, they'll ask like 6 questions. All right, and the last question is always having to do somehow with the domain. Okay, can we reference what our domain values are? So let me give myself a little bit more room here with this thing. All right, so we've got these two functions. And it just says find the functions f plus g, f minus g, f g, and f divided by g in our domain. So let's do that first. You've got options. If you want to go through and find the domains of f first and g first, that's fine. If you want to find the sums and differences first, that's fine. Let's just go ahead and find the sums and differences. If I want to find f plus g of x, okay, I'm going to take my f function, 1 over x minus 2, and I want to add to it my g function, radical x. And there we go. Okay, we are done with finding f plus g. That's pretty straightforward. Okay, now if you wanted to, could I do common denominator stuff? Yeah. Whether that's necessary or not, I guess would be kind of a situation type thing to analyze. Okay. Right now, I'm not really worried too much about combining like terms and that kind of thing, or an LCD. If I want to go f minus g of x, okay, order matters here. So f was 1 over x minus 2 minus n root x. Is that pretty easy? All right, I'm gonna do one that's not up there. I'm gonna do g minus f because that's different, right? G minus f would be root x minus 1 over x minus 2. Let's go f times g. F times g of x is going to look like 1 over x minus 2, that's f, times root x. I think it does make sense, at least in this one, to rewrite this as root x over x minus 2. Stop me if I'm going too fast or confused about something. Is that okay? Okay, now let's do, I know we only want f divided by g, but let's find both. So f divided by g of x, okay, would be 1 over x minus 2 divided by root x. Okay. Now, can we simplify that? We have division by a fraction, right? Let's multiply by a reciprocal and multiply by 1 over root x, right? So top. And that's going to be 1 over root x times x minus 2. And we'll see now g of x, or g divided by f of x, would be g is root x. Okay. And then f is going to be 1 over x minus 2, right? Can I change that to root x times x minus 2 over 1? That make sense? So it ends up just being root x times x minus 2. These, though, guys, this is important. We don't want to just jump straight to the simplified version here. I want to be able to look at this and realize what we're really doing with both these when it comes down to the domain. Okay? Because even though we've got some simplified versions of what's going on there. The idea is when we are evaluating these two functions, we can only use x values that exist for both functions. Does that make sense? Okay. So we're going to go through the domain. We'll kind of talk about that as we analyze this and get to it. But let's. I'm just going to. Is it okay if I delete this phrase out of here? Give myself a little bit more room. I'm going to find the domain of f. Okay. And you can label these how you want to. I'm going to try to use what our definitions above said in the previous slide. And they said the domain of f, they let that be, they call it A, right? Does that make sense? Okay. Now, what is the domain of f? What values are we allowed to use for f of x? Everything but 2, right? Division by 2, or using x to be 2 would give me division by 0, right? That's a problem. So everything but 2. So where we write that interval notation, we negative infinity up to 2, union to a positive infinity, right? Now, I'm going to find the domain of G, which the above statements call it B, right? We call that this set of values capital B. What values am I allowed to use for G? Okay, be careful. Because when you say positive numbers, I don't incorporate 0 with that. Okay, so the safest thing to say would be our non-negative numbers. Okay, 0 a lot of times is not defined as being positive, but we usually call it a non-negative. Okay, it's not kind of 0. It's nothing. I don't determine whether it's positive or negative. Okay, we just say it's not negative, which means then it's not necessarily positive either, right? Okay, so 0 to infinity including 0. So now, when we want to know what is A intersects B, the idea of that, guys, is if we look at the graph of these, look at the graphs on top of one another. So here's my another line. Okay? Try to graph the blue one. Graph of the blue one is going to look like this, right? Got value of 2 right there. Should be an open dot at 2. And it should be everything to the left of 2, right? And everything to the right of 2. That's the A set. Okay, or the domain that came from F. When I look at B, okay, now I find 0. Maybe 0 is right here. All right, what kind of dot would I use at 0? Closed. And there's going to be those values there, right? That symbol means intersect. Intersect means the overlap, right? So we're going to look at these and we're going to decide where do they start overlapping. It's the first number that you see up there where they start overlapping. Okay, 0. So right there, they both have 0 on them. Okay, so I'm going to include 0. Okay. Now, the other place that I have an issue would be right here, correct? At 2. Do they both have 2 on them? This one does, right? Because it's essentially closed in. Is this one open or closed? Open. So it's 2 on both of them. No, it's only on the red one, right? So can I keep 2? No. So we got to kick 2 out. So that's how we do that. Comma 2, parentheses. And then we'll put a union. 2, And now where else do they start, or where else do they overlap? All the way to infinity. Okay? So, which my screen was about twice as big as it is. We're out of room here. All right, so that there is the domain of f plus g. Why does that make sense? Think about why this has to happen. We said in order to evaluate f plus g, okay, then this x value right here has to be an input that generates an output for both f and for both g. Well, that's f and that's g. If I plug in 2 right here, what do you get? You get 0 on the bottom, but what's 1 divided by 0? Undefined. Well, what's undefined plus radical 2? It's undefined, right? We don't know what that is. There's nothing to add to that radical 2. Does that make sense, everybody? Okay. For the same reason, if I would have chosen like a number like negative 8, okay, plug negative 8 in here, I get 1 over negative 10, right? So negative 1/10. But then when I come over here and plug in negative 8 here, I get pi radical 8. And when I add those two things together, it does not produce a real number. And that's what we're looking for. We're trying to realize that when we're doing these function evaluations, when we're adding them, subtracting, multiplying, dividing them, a real number plus a real number should give me a real number. A real number times a real number should give me a real number. Does that make sense? Okay. Let's call it that feature that when we talk about that, when I add two numbers together that are real numbers and I get a real number, that's what we call a closed idea within that operation. Okay. Eventually, if you start getting into more complex mathematics, you start talking about what we call fields and rings and stuff like that. I believe that'd be a closed field when we take addition of real numbers. All right, so if that's the domain for f plus g, what's the domain for f minus g? Is it different? Oh, can't really see that. It's not different, right? Because if I look at this, we still can't use 2 here, and we still can't use negative numbers here, right? So the domain for f minus g is still that thing right there. Okay? What about g minus f? Is it still the same thing? Absolutely. Okay? What about d? What about f times g? Do I still have to have a number equal to 0 or greater here? Do I still have to kick out 2 there? Absolutely. Okay? So the domain, once I found it for f plus g, it's the same for f minus g, same for g minus f, same thing for f times g or g times f. Okay? So those domains are all the same. All right? Now, I want to go, I just want to give myself some more room. So let me insert another slide. I don't know if I can cut and paste it with that. Okay, that'll work. You guys read that? All right. We had, all right, so I want f divided by g. I want to rewrite that one, f divided by g. And it looked like, so f was 1 over x minus 2, right? G was divided by root x. We simplified that. We simplified that as 1 over root x times x minus 2, right? Okay? And we had g divided by f of x, and that would have been root x over 1 over x minus 2. We simplified that, and it gave us root x times x minus 2. Okay? When I want to find these domains, remember the domain A intersects B, that ended up giving us, I'll write this down the bottom, A intersects B was 0 to 2 union 2 to infinity, right? Think about this, okay? And in this one, it doesn't matter, but I would go back to this because the idea, the logic says that this is the domain of F. This is the domain of G. We need to make sure that when we look at these things, okay, that we do not divide by the domain of G. Okay? I cannot divide by 0 right there. Does that make sense, everybody? Okay? So, because this cannot be 0, but if I were to look at the domain of G, 0 is part of that, right? So what do I need to do down here in my overall domain to address this situation? Change that bracket to a parenthesis. Okay? Change that bracket to a parenthesis. Now this is where I don't like looking at the simplified version, right? Because it's going to get you in trouble sometimes. If I look at this simplified version right here, does it look like I should keep 2? Yeah. Okay. It looks like if I evaluate that simplified version at 2, I get radical 2 times 0, right? I should get an output of 0. But I know we shouldn't have used 2 at all because when we had it in this version here, could 2 be allowed to be used in that fraction right there? No. Okay? So because 2 was not defined for that function there, it's not going to be defined for this when I simplify it. Okay? If it's kicked out here, it can't reappear when you do simplification. Does that kind of make sense? You kicked it out for a reason. So we need to make sure we kick it out. So, do I change anything down here then? No. So this is a situation where the domain of both of these, F divided by G and G divided by F, are the same thing. Just be careful with that because it won't always be the case. Okay? For instance, let me give you something that would be kind of a situation that we would have to address. Let's say that I have, let's just say f of x is equal to x plus 1. Let's say g of x is equal to x plus 3 over x minus 2. And I do f. So this is linear. This is a quadratic. Okay. So the domains of those are both polynomial. So the domain, let's write this, domain subscript f, that would be all real numbers, right? Domain subscript g, again, all real numbers, right? Okay? Now if I did f divided by g, and let's look at that, f divided by g would be x plus 1 over x plus 3, x minus 2, right? So if if the domain of f divided by g is the overlap of those, well, what's the overlap of all real numbers? All real numbers, right? Okay? So that overlap, so domain of f intersects domain of g would again be all real numbers. But now look down here, it'd be all real numbers except for what thing? Yeah, so the domain of f divided by g would be, I'll just write it this way, all real numbers except -3 and +2, right? Let's change this. Let's go g divided by f. That's going to be x plus 3 times x minus 2 over x plus 1. What's the domain now of g divided by f? Except for -1. Good. Okay. So you see how those domains were not the same? All right. So when you are dividing, order matters. Okay. Occasionally you might just run into a situation like this one, where the domains indeed were the same, but generally speaking, that's not a fact. Okay. All right. So the reason I wanted to try to cut and paste that stuff earlier is because they were asking us. They were asking us eventually to find f plus g of 4. F plus g of 4. And talking about what f plus g of 4 is, we've got two options, guys. We can actually take and realize that that means f of 4 plus g of 4, right? So I can come back up to this thing here and evaluate at 4. What would you get if you evaluated that at 4? You get 1/2, won't you? Okay. Then it says evaluate g of 4. What happens when you evaluate g of 4? 2. It says add those together. What do I get when I add those together? 2.5 and 5/2, right? Just because we didn't introduce the square root, so the assumption is it's positive. If we were introducing it, then it'd be plus or negative. Is that all right, everybody? Can we do it that way? Do we get the same thing if we come to this function right here and evaluate that one at 4? Yeah, it's really the same procedure. I'm pointing 4 right here. I get 1/2. Pointing 4 here, I get 2. All right. The purpose maybe for having this one is again the technology. If I was going to evaluate at 4, 5, 6, 7, and 8, maybe I want to type that into Y1 and my calculator is going to take it. Okay. And my technology will allow that to happen. We can do the same thing with f minus g of 4, f times g of 4. Okay. Let's do f times g of 4. If I do it here, okay, I get 2 up top, right? Okay, put 4 in there, put 4 in here, what do you get? To the bottom, right? So f times g of 4 gives me 1. Well, is that the same thing that I would have gotten if I were to evaluate it up here at 4? If that was 4, it gave us 1/2, right? Here it gave us 2. What's 1/2 times 2? Still this 1, right? Okay. So the individual evaluation, okay, take an input value, find the output for f, then find the output for g, and do your operation after you found the two outputs. It's fun. Or if you want to create your new function, f times g, take your input and run your input through that new function, you should still get the same output, okay, that you did when you, or that you got when you went through both functions separately. Is that all right? All right. So let's analyze this graphically. Okay, a little bit of time to do this. F of x was 1/x minus 2, right? Okay. G of x was equal to square root of x. All right. So we're looking at those two functions. Now, what happens? See if we put the names on these. There's G. Well, it won't let F slide down. So that's G, so you know the green one's F, right? Up. Close enough. All right, so the idea here, guys, is if I were to find F plus G of 4, what are we really doing? Well, that's F of 4 plus G of 4, right? Well, F of 4, that's the Y value when X is 4, right? That's the same thing as that is, but it's for different terms. So go find 4, X is 4 right there, okay? Oh, freeze on me. There you go. So it's saying when X being 4 is that line right there. Okay. So it's saying take the Y value of B and the Y value of A, add them together.
Hello, please pardon the interruption. I have several people on a list here that I'd like to come to the office. Keaton Phillips, Ashley Donano, Armando Garcia, Zachary Garza, Briston Brock, Miguel Reyes, Taylor Williams, Cameron Wallace, Ainsley Miller, Maddie Renner, Isabella Price, Callie Armstrong, Jasmine Glabelt, Haley Hitchum, Paige Williams, Emily McNett, Amy Fowler, Riley Hyland, Kylan Shadowlog, Natalie Crow, Thomas Douglas, Derek Inskeep, Ireland Lawrence, Damian Moss, Braden McCoy, Britton Hall, and Annabelle Burkholder. Please come to the office.
All right, so when we're adding F plus G, okay, the idea is for the same X value, you're adding these Y values, and it gives you 5 halves, right? So at 4, if I was to plot 5 halves, which is 2.5, correct? We'll plot that point right there. And let me show you what happens when I ask this thing to graph F of X plus G of X, okay? You see how that blue curve has that point right there on it of 2.5? Does that make sense? Okay? So that blue curve is the rule that we developed algebraically when we went through and we combined the functions with addition. Okay? But it's simply taking all the red points and all the green points and adding them together for those respective X values and plot. Okay? The idea is if I take, F of 0 divided by G of 0, see what it gives me. It gives me an undefined value, right? It gives me negative infinity. Does that convince you that when we looked at our domain for F divided by G, we had to kick out 0? Okay? For the same reason, F divided by 2 divided by G divided by 2 gives me that there. Okay, but if I look, I just want to show this to you. If I look at what was it? I think it was G divided by F, so G of X divided by F of X. Okay, now it's not going to evaluate it for me, but let me put that curve on there, and if I put this curve, square root of X times X minus 2, is that the exact same thing? Okay, but on this one, 2 is not a problem. Does that make sense? Okay, but on this one, if I evaluate Q of 2, that's a problem. That should not happen. Okay, should give me undefined. I don't know what GeoGebra is doing there. There is a 2.7 on website.